It's time for the dreaded projectile unit, which all students dread, because now we are getting ready to do X and Y movements simultaneously. And believe it or not, students have a hard time with connecting the two. I'll try and make this as straightforward and as easy as I can. So first of all, let's start off with the definition of a projectile. Projectile is any object that is moving and affected by gravity only. I'll show you a graphic of that in just a moment. So before I do that, I want to tell you that the motion is determined by movement on the x-axis at the same time as movement on the y-axis. So let me give you a little time to write all that down. You can pause the video here if you need to, but let me show you an image of what I'm talking about. So this is an example of a projectile. This is the simplest example of a projectile. We're going to start horizontally because that seems to be the easiest, and we'll attach our vectors unit to this at the end, but I'll show you what I'm talking about. Here I have a cannon. So I'm going to shoot this cannon, and it's going to shoot a cannon out horizontally, but as the cannonball is traveling horizontally, gravity grabs onto the cannonball and begins to accelerate it downward. So we have motion on the x-axis and on the y-axis. What's really interesting are some really important facts that are non-intuitive to students, but once we practice with this a little longer, you'll see that it makes sense. First of all, the first thing I want to say is, and let me pull out this piece of paper, and again, like I said, this is counterintuitive. The first thing I want to say is that the velocity on the x-axis is constant. It doesn't change. Once that projectile is launched, any motion horizontally any velocity on that horizontal plane stays the same. And I'll give you an example of that. We're going to do some sample problems also. And that is counterintuitive to most students. They think once the ball is launched that the velocity slows down. In our perfect world, it doesn't. We haven't talked about air resistance. We're not going to worry about terminal velocity, none of that. Our world is perfect. We live in a vacuum. There is no air resistance. And with those two parameters defined, then the velocity on the x-axis is constant. Whatever speed it comes out at, it's going to stay at that speed, at that velocity. The second thing that's kind of counterintuitive is that the velocity on the y-axis is not constant, meaning as the ball is dropping, it's getting faster, faster, and faster. That's because gravity grabs a hold of it and pulls it down to earth. And you all know that the longer it falls, the faster it gets. And we're going to do the math behind this. So let's go back to our image here. I have a cannonball. It's sitting on a cliff. Or a cannon. It's sitting on a cliff. It shoots a cannonball. So I'm going to draw my velocity vector, and I'm going to indicate them with arrows. And y'all should be used to that by now. We've done a lot of units, a lot of practice with vectors, and you know that a vector is an arrow. The way it points is the direction, and the length of the arrow is the magnitude. So I'm going to put an arrow out here, and this is my velocity on the x-axis. Velocity is a vector. It has a magnitude. It has a direction. So I can symbolize it by an arrow. And as the ball is traveling, the length of that arrow and the direction it points does not change. This signifies that that velocity is constant. It doesn't change. Now the velocity on the y-axis here points down. So I'll say velocity on the y, and I'll do a downward arrow, points down. And as the ball falls, that arrow gets longer and longer and longer, because the longer it falls, the faster it gets. And I am designating that by changing the lengths of my arrows. So the velocity on the x-axis is constant, and you can see as the ball is projecting, it is moving away from its original location, and it's moving away at a constant rate. As it's also projected, it is falling toward the ground, and it is not falling at a constant rate. You have to keep those in mind, that way you know what equations to use. Another thing that's kind of counterintuitive to students is what happens when you change that launch velocity. So I have the paths of 3 different projectiles. I have D, I have E, and I have F. And let's say I launch D, velocity on the X, at 3 meters per second. I have a launch velocity here on the X at 5 meters per second. And I launch this velocity here on the X at 7 meters per second. Now what most students think is that the faster you launch the projectile, the longer it stays in the air. That is not true. The faster you launch a horizontal projectile, the further away from the base it travels. But they all hit the ground at the same time because the time in the air is based on the height. And as long as this height is the same for all 3 of these projectiles, they will all hit the ground at the same time. And again, that is counterintuitive. So time in the air, oops, time in the air is based on the height. That is for a horizontal projectile. We'll get to vertical in another video or two. But horizontally, if I shoot something horizontally, the time in the air is based on the height. You need to remember that. Alright, so now let's talk about the equations that are involved. They're actually fairly simple. You already know them. We're just going to apply them in 2 dimensions. So here are the equations that are involved. We have velocity on the x is equal to delta x over t. That is the only one for horizontal motion. For the horizontal motion of this projectile, which is this way, since it's constant, we use the constant velocity equation. That is it. Okay, so velocity on the x is delta x over t. We have velocity on the y is the initial velocity on the y plus gt. Remember, the speed on the y-axis is changing. It's accelerating, so we have to use this equation. We also have the height. The height is equal to initial velocity times on the y times time plus 1/2 gt squared. You should know this one. And we have a velocity equation, which is velocity on the y final, let me put an F, is equal to velocity on the y initial squared, that is also squared, plus 2g delta y. Now what is interesting is that the initial velocity on the y-axis for a horizontal projectile is 0. Initially, the ball is shot out this way, not this way. So initially, the velocity on the y-axis is 0. Then gravity grabs a hold of it and begins to pull it down, making it go faster and faster and faster. This is for a horizontal projectile. Again, we'll get to vertical later. So this is key. Velocity on the y is 0. Well, knowing all that, then all these equations become really simple. I can get rid of that, I can get rid of that, and I can get rid of that. So that's why I always like to look from the top coming down, because the initial velocity is 0, and you should know this from free fall. So when we evaluate projectiles, you have to evaluate it separately. First, you can look at what's going on the x-axis only and then the y, or you can look at what's going on the y-axis and then the x. All right? You look at them separately, not together. I'll show you what I mean in a second. And the other thing that's important is that time is the same for both axes. If it takes 3 seconds for the ball to drop and hit the ground, then this ball only has 3 seconds to travel out forward before it hits the ground. So the time unifies the x-axis to the x-axis to the y-axis. Time is the same for both. Alright, if you want to pause the video for a moment and take in what I said, you can do that. I'm going to do a couple of example problems. And I'll put a link to this sheet up on my calendar, and if you want, you can print it out and follow along with me. So let's take a look at some horizontal projectiles here. Here's the first one. It says a ping pong ball rolls with a speed of 0.6 meters per second from the edge of a table, and the table is 75 meters tall. The ball rolls off the table and plunges to the ground. 2 questions. How long is the ball in the air? And B, how far out from the edge of the table does the ball hit the ground? If you're not sure what it looks like, let me draw a little diagram here. I have a table, I have a ball, it goes out this way. It's launched horizontally from the edge of the table. This is 0.6 meters per second. Okay, that's the way it goes. The ball's going to travel and then it's going to hit the ground somewhere down there. So we're trying to find how long before it hits the ground and how far out from the edge does it hit. That's what we're looking for. Well, let's list what we know. We know a couple of things. We know that the velocity on the x-axis is 0.6 meters per second. We know that the initial velocity on the y-axis is 0. We know that gravity is 9.8, and we know the height of the table. Height delta y, sorry about that, delta y is 0.75 meters. How long does it take, or how long is it in the air? We're looking for time. And according to my equations, let me find that sheet again. We're looking for time. Well, I have a height, I know gravity, I'm looking for t. Let's use this one and rearrange it. And when we do, we get t is equal to the square root of 2 delta y over g. This should all be reviewed. None of this is new. Really, none of it should be new. We plug in our numbers. Oops. 0 times 0.75, 9.8. And for time, what do I get? I get 0.3 seconds, 0.39 seconds. That's the first one. And the other one is how far out from the edge. Well, velocity on the x is constant. I have only one equation to use. Vx is equal to delta x over t. So delta x is equal to the velocity on the x-axis times the time. Delta x is equal to 0.6 times 3.9. And from the edge of the table, I get 0.234 meters. Alright, I use the same time because the time it takes to hit the ground is the time it takes to travel forward. That's straightforward. I think I have time for one more, so let's do one more. This is a 3-parter. Okay, a diver leaves a springboard horizontally with a velocity of 2.8. Velocity on the x is 2.8 meters per second. I know the height, delta y, is 3 meters. And it wants to know, let me write here, I know that g is 9.8 and the initial velocity on the y is 0. These are all the things I know. That's v and that's an I, if you can't see it. Alright, how long does it take? How long is the diver in the air? I'm looking for time. I can use the same thing I used up there. T is equal to the square root of 2 delta y over g equal to the square root of 2 times 3 over 9.8. T is equal to 0.78 seconds. Number 1. Number 2, how far out from the edge does the diver land? Again, I'm looking for how far out from the edge. I'm looking on the x-axis. Velocity on the x is constant, so I can use delta x, vx times t. Velocity on the x is 2.8, and the time before she hits the ground is 0.78. So from the edge of the board, she is 2.18 meters. And last, this is a little interesting, is how fast does she travel when she strikes the ground? Well, you have to be careful, because I did say that her velocity on the x is constant. And I know that number, it's that one. But she also has gained velocity on the y. It starts out as 0, but as she's falling, it gets faster and faster and faster. And when she splashes into the water, those two meet. Oh my gosh. It looks like we're about to use vectors, because she's going to strike the water at that point where the two velocities come together. Well, I have a velocity on the x, I have a velocity on the y. I'm trying to find this final velocity, the addition of the two of them together, which means I'm going to have to use Pythagorean theorem, is what that says. It looks like this is the result of this velocity on the y combining with this velocity on the x. So the first thing I have to do is find the velocity on the y. Well, initial velocity on the y is 0. So I can say final velocity on the y is g times t. I use that one right there. Gravity is 9.8. And the time till she hit the ground is 0.78. So velocity on the y is 7.64. I have this number. I have this number. I can combine these two using Pythagorean theorem to get that number. So my resultant velocity, which you guys know is r, is the square root of velocity on the x squared plus velocity on the y squared, which is the square root of, what is that, 2.8 squared plus 7.64 squared. And when all is said and done, I get 8.14 meters per second. That's how fast she's going when she strikes the ground. This is the one thing that could be new, but we've done vectors with distances. You can also do them with velocities, because velocity is a vector. We'll talk about this more when you guys are done watching the video, but it looks like I am over time. So I will stop, and at this point, you should be in class, and I will take questions. So good luck.